Hi everyone, and welcome to our course. I would say this is like my favorite topic of the whole course because this is where is my research, where is my interest, which is the application of machine learning in outdoor insulators assessment. I use machine learning for some other applications as well in terms of the asset assessment, but I thought instead of spreading the discussion of the application of machine learning. Let us focus on the outdoor insulators and see some of the applications. And I selected the application in such a way that it covers good amount of spectrum of applications in outdoor insulators. Also, I will try to do something in this presentation, which is I will do some demonstrations. So I will use Weka, a very good free to use software to apply machine learning, and I will show it to you how it's very easy to use. Even if you don't have any background, you can easily use it. This is basically just a photo of one of my students using RF antenna to detect damages in ceramic insulators. That was done in conjunction with Clitrix. In there, they have an outdoor yard for testing, so we used it there. Okay, so today we'll talk about the following points. First, I will give a very slight introduction about machine learning. So in case you don't have any idea what is machine learning, we will just cover that very briefly so that you will understand the concept of machine learning. Then we'll be giving examples of the machine learning applications for outdoor insulators. We'll have examples from ceramic and from non-ceramic. Now, last week, we covered the ceramic and non-ceramic insulators. We saw their problems, their issues. So today is an application of last week problems. We're trying to diagnose, trying to condition monitoring these insulators when they are subjected to some of the issues we covered last week. This is why I thought it's better for a continuity, talk about outdoor installations in one presentation, talk about the application of machine learning in the other presentation, so that they basically come together, and whatever I mentioned in outdoor installations can be applied to cables, applied to transformers, circuit breakers, and so on and so forth. And finally, I will end our class today by talking about what is the future for this technology, where people are heading, what are the challenges that is coming ahead in that specific field. So let's start with introduction about machine learning. The process of machine learning starts from collecting the data, then pre-processing the data. Sometimes there's need for that. Then something called feature extraction. Then we will have the feature vector formed. We'll talk about all these things in details. Once we form our feature vector, then we use some machine learning algorithms for the classification, and then will be our decision. What is the defect type? What is the problem of the insulators that we are inspecting? So we'll start with collecting the data. Now, before we start collecting the data, you have to know what type of data you are working with. And this is something very important, that understanding the physics of the problem is extremely important. Why? Because if you don't understand the physics of the problem, you will not use the correct sensor. You will not understand what are the limitations of that specific sensor, what it can measure, what it cannot measure, how this physical phenomena, if I use that specific sensor, should look like. So it's not just anyone can just collect some data and apply machine learning. It has to be someone who is expert in the field. The focus for us as power engineers is on understanding the physics of the problem. For us, the machine learning is just a tool. We use it as a black box. I don't care if I know the coding or I use something like Weka to apply it. That's not the issue for us, as far as I understand the physics of my problem. And I'd like to stress too much on this because I have seen many papers sent for publications, I review them myself, people just they think that application of machine learning is an objective. So they just gather any data, some of it doesn't make any sense, and then apply machine learning because it's like a fancy word and get some publications. And that is wrong. We have to go back to the fundamentals. We have to make sure that we understand the physics of the problem before we proceed further. Now, the first thing we need to understand, what is the insulation system I am monitoring? Is it a bushing? Is it an insulator? Is it ceramic? Is it non-ceramic? Why? Because the problems, as we have seen before, they are different. They are not the same. So we have to know what is the insulation system of interest. Second, what exactly I want to measure? Do I want to measure partial discharge? Do I want to measure dry band arcing? So what exactly I want to measure? Third, what is the sensor or sensors that I want to use? I want to make sure that I use the sensor that can capture this phenomena. For example, if I am measuring a low frequency phenomena, like a dry band arcing or leakage current, this is a 60 hertz and with some multiple harmonics. I cannot use an RF antenna, which has a very wide frequency band and cannot detect low frequencies. This is not the right, it's not the correct type of a sensor. But maybe an IR camera could be a good sensor. Acoustic could be a good sensor. If I am trying to detect some internal defect in the insulator, definitely UV ultraviolet camera is not the right choice because I will not be able to see anything. So understanding the physics of the problem, understanding what exactly I am looking for is very important to decide the number of sensor or the type of the sensor. Finally, what is the objective of the monitoring system? What exactly I want to do? Do I want to, for example, monitor dry band arcing? Do I want to, for example, monitor if the insulator is approaching failure? So what is the objective of my monitoring system? In very simple language, it is the monitoring system or collecting the data. We have a sensor. We have, sometimes we need, sometimes we don't, an amplifier and or filter. And then we have the data acquisition system. Now, something very important here, that you have to have a good frequency matching between these three components. If there is no good frequency matching, as we will see, we will get bad results. For example, this is an RF signal used by similar antennas, okay? And this is the frequency content of that RF signal. Now, this signal number one, this is signal number two. So similar antenna, and they are measuring the same thing, which was partial discharge. Now, when you look here, in the first one, I used a 60 megahertz bandwidth oscilloscope. So the oscilloscope can handle up to maybe 100 megahertz. That's it. Then it will attenuate everything. In the second one, I used a 2 gigahertz bandwidth of an oscilloscope. So this is something very, very important, that there is a matching between the phenomena and the measuring system. Why? Because the RF antenna can measure in the gigahertz range. The partial discharge is in the 100 of megahertz to the gigahertz, okay? But when my oscilloscope is only 60 megahertz, you see here, I only captured very, very little information about the signal. That is zero. Zero, why? Not because there is no information, because my measuring system failed to detect that because it's very weak in terms of the bandwidth. Here you look, you see the signal power where it's concentrated. It's concentrated in the gigahertz range because my oscilloscope can do that. So very important before you select your measuring system to understand what is the frequency content of my sensor, my phenomena, and my measuring system. Here is another example here about the acoustic signal. The first one, we have a sensor that is working between 20 to 80 kilohertz. Again, this is just measuring the outside environmental noise. And here is from 100 to 450 kilohertz. Both of them are ultrasonic sensor, but this one is at the edge of the ultrasonic sensor. So here we try to run a motor, okay? And we found that this sensor picks a lot of noise. Why is that? Because the hearing voice is between 20 hertz to 20 kilohertz. And that sensor is at the verge, so it will be pick a lot of noise. But that sensor, the other sensor, the frequency spectrum from 100 kilohertz to 450 kilohertz, far in the ultrasonic range. See, the signal is 10 to minus 3. It doesn't detect anything. So that sensor, if you have a noisy environment, it's very important to use something like that so that you will not be picking up the noise. So understanding the environment also is something very important for selecting your sensor. Second, after I collect the data, I need to pre-process that. What do I mean? Pre-processing is, for example, denoising. Many times in the field, you measure something, you measure using RF antenna or you measure using acoustic. Sometimes it is corrupted with noise. You need to denoise the signal. This is a partial discharge measured at the lab, okay? But it was very, very small amount of partial discharge. And for measuring this, we use high frequency current transformer. And we know that the high frequency current transformer has a low signal to noise ratio. As a sensor by itself, it's a weak sensor. Unless the partial discharge is large enough, it will pick something like this. Okay, so it's not very clear for us if this is a partial discharge or it's a noise, but we know that there is a partial discharge here because we use the classical PD to measure it simultaneously. So now we applied some advanced data signal processing techniques to extract the partial discharge from the signal. Now, sometimes I don't need that. I don't need to extract the partial discharge because the signal itself is high enough. It doesn't need any filtration. So this pre-processing sometimes is not needed. This is another pre-processing we did for acoustic signal. So this is the original signal, and this is the denoise signal. This is an ultrasonic PD signal. Sometimes the pre-processing needed for images. Sometimes we take images. These are some images taken to do some classification for the hydrophobicity. So this is a pure research project. I did it around 9 years ago. So we have tiles coated with RTV coating, and you can see here these are tiles basically here. So we need to extract these images. So we extract the image from this, and then we apply contrast level adjusting, and then denoising and using the gray level thresholding. So you can see here, this is much clearer signal to do any extract feature from it, apply machine learning than the original signal. So pre-processing also when you have images, sometimes it's very important. Then we have the feature extraction and the feature selection. This is something extremely important. Now, you get a signal. Now, the signals you get, I have seen some examples. It could be like 1D signal, like a signal coming measured by a current transformer or an RF antenna or acoustic. This is called 1D. Or could be a 2D, which is an image. Okay. Now, these signals, you cannot just feed it to the classifier. You have to extract some feature from it, some numbers. Okay, so there are two main classes of features you can extract. One of them is a class of statistical features. These are just two examples, the kurtosis, okay, and the skewness. The kurtosis is how wide or how narrow is the distribution of your data. The skewness, how is your data skewed to the right or to the left from your mean. So these signals give you some sort of feeling about the signal, how it look like. So we will show you some example how we use these features. More importantly, and give you more information, is the spectral features, like the discrete Fourier transform. So if you take the frequency content of the signal, you can extract some of the frequency contents, or if you use some advanced technique like the wavelet, you can make the resolution of the frequency and time at the same time. Now, if you don't understand what is wavelet, that's not the point here. This is just an example. But what I want to say here, you need to extract features. from the signal. You cannot use the raw data as it is. Okay. Now, for example, if you take the f of t, you will have too many signal, too many frequency components, which will lead us to something very important. Or when you do the statistical features, are those features important or not important? How do I know that if these represent the phenomena I am measuring or does not represent that? This will take us to something called feature extraction and selection. There are different techniques. One of them is the stepwise regression. It can be used and to see the significance of these features on the phenomena that you are measuring. And basically, they are statistical measures. It will tell you, okay, you have, for example, you are measuring, let's say, a signal. Okay, so this signal is, let's say, acoustic emission signal. So you take, let's say, you find from here 10 different frequency components. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 features. Okay, it will tell you, okay, the most important feature is number 5, then number 6. So this is the best one. The second, then third, and the second, they are almost the same. The others are not very, very important. So maybe you select the first 2 or the first 3 features. You don't need to select the whole features. Another technique is called the principal component analysis. This one is basically a technique that you take the features to another dimension, a reduced dimension, and use that reduced dimension and select the best combination of the feature to give you that new features. Okay, so that's how I select my feature. So now I have my feature vector. I did the measurement, selected the features from these measurements. Now I am ready to apply it to machine learning. Now there are different techniques we can use. We have something called supervised learning and unsupervised learning. In supervised learning, we have classification and we have regression. Today, we'll just talk about the classification problem. But let's understand first, what does it mean to say this is a supervised learning or it is unsupervised learning? When you have data, we call them labeled data. What do we mean by labeled data? That you know that, for example, my problem is trying to find that the PD, the partial discharge I am measuring, is it coming from a void or is it coming from a sharp point or is it coming from surface discharge? So that is my problem. So is it from a void, sharp point, or a surface discharge? So what I do, I go and I need to create data myself. I create controlled PD using void. So we'll have PD coming from void. And I will have many signals from this. And then PD from sharp point. And I have too many signals. And PD from surface. And similarly, I will have too many signals as well. So I have what we call labeled data. I will take the data here and I will basically use it for the training. But the data I am using, I know what it does represent. This data represents a void. This data represents a sharp point, and this data represents a PD surface. This is called labeled data. Now, this is called a classification problem when you basically use the data to classify either, like, for example, type, void, internal, external, or high, medium, low. So they have this discrete description. Regression, when you want to predict a number, like, for example, you want to predict what is the ESDD level. So it is equal to 0.16 milligram per centimeter square, a number. Okay. A classification would say that the ESDD is high, medium, low, very low, for example. Now, in outdoor installations, because as I said, I will select classification problem only today's lecture because most of the practical problems we have in the outdoor installation, they are classification problem. The second category of learning is called unsupervised learning. Now, unsupervised learning, basically you just give the classifier data that you personally, you don't know from where it comes. Let's say partial discharge, you collect them from different sensors. You said, okay, I have this, but I don't know if this is coming from what. Even in the training stage, and we'll talk about what we mean by the training stage, I don't know exactly from where this data comes. So you will have some technique like the clustering. You cluster the data. You will see, okay, this data belong to one cluster. This data belong another cluster. This data belong to a third cluster or a fourth cluster. Then based on your experience, you would say, okay, this cluster most likely is a PD from internal, based on where this cluster is located, and so on and so forth. Okay, so now it comes to the classification. We want to do some classification problem. Now, in the classifier, we will select a classifier, and there are tons of those classifiers. As a rule of thumb, there is no magic classifier. There is no classifier that works for all problems. Each classifier has certain pros and certain cons. And based on the data itself, you will find that certain classifiers work best for this data. As a matter of fact, application of machine learning in the classification and in the diagnostic is both science as an art as well. So it has an art element in it. It's not just pure science that, okay, use this formula, you will get this. No, you have to play with the data. You have to do a lot of manipulation and looking around to find what is basically the best classifier for you, as we will see in the exercise that I will do with you today. Okay, now we have these classifiers, but before that, how to handle the data. I'm talking about supervised learning, only classification. So let's say I have 3 class problem, A, B, C. So this A, B, C will come to it many, let's say, signals. So class A, now class A could be, as I said, could be a class of partial discharge, or it could be a class of the ESDD level, or it could be anything else. Okay, so we have 3 class problems, and under each class you have signals, 1D or 2D. It depends what sensor you have used. And then I extracted the features from those sensors. Okay, so I have data here, data points from 1, 2, 3 until n. And I want to apply my machine learning algorithm. So what we do, we split the data. Let's say 80% of the data I will take for training. So I will be training my model using this data. And I will take, let's say, 20% of the data for testing. So I will not use this for training. In a simple language, imagine that you want to teach a kid what is the difference between an apple, an orange, and a banana. Okay, so you bring images of apple, different types of apples, different types of oranges, and different types of banana. And then let's say you have 100 images of each. You say, okay, we take out 10 or 20% of the images, put them on the side, and then start teaching them. This is an apple. This is an apple. And you show them different types of apple, colors, sizes, types, and so on and so forth, so that the kid will be trained that, okay, whenever they see this is an apple, then you show them the orange, come up with different sizes again, maybe different grades of orange, so that is well trained. Then the same thing for the banana. Once you train the model very well, then you need to test the model. So you bring those 20% of the data, in this specific example, those 20 images, and show it to the kid that you are training, and see if he or she can, how many of those images they can basically identify. And that will judge if your training was good or was not. And this will lead us to multiple topics in machine learning. I will just mention them very, very fast. Sometimes you have a biased learning. How is that? When you give them just 100 image of only one type of apple. So if you bring that type of apple, easily the model can identify. But if you bring, let's say, a green apple, will not be able to identify that. So you have to make sure that your data actually is done at different conditions so that you have a model that is general. You don't want to build a good model that give you high accuracy at specific conditions. Let's talk about partial discharge. Imagine you want to do partial discharge classifications, and then you give them the partial discharge at one specific voltage, at one specific insulator, at one specific distance between the sensor and the insulator. And you take too many data at these specific conditions, and then you do the classification. Wow, you get a very good result. Your model is doing very well. But then you try to test the model at a different distance, at a different voltage level. It doesn't work at all. You start, why? Because your model was trained at a specific condition. You have to make sure that your model is trained at multiple conditions so that you have a robust and a good model. So that's in a nutshell what is machine learning all about. Having a generalized model is one of the biggest challenges in machine learning. Having a high accuracy on a biased model is very easy to be achieved, but that's not your objective. Your objective always, you're trying to, you have a model that is really generic, that can be applied for many applications. Today, I'll talk about only 3 classifiers, okay, in a very, again, generic way, and I try to make things away from the math so that you understand the concept, because as I said, our objective as power engineer, not to dig deep in the machine learning. Okay, there are some people who are working on that. Now, if you have a hobby and you want to learn about it, okay, that's okay. But as a power engineer, the objective always should be to understand the physics of the problem and deal with the machine learning as a black box, unless you are really interested to dig deeper in this specific topic. So we'll start with the mother of all machine learning algorithms, which is the artificial neural network. The artificial neural network is being basically inspired by how our brain works, how our system recognizes if something is, for example, is hot or is cold. There are neurons in our we have sensors all over the place. We have our vision sensor or for our touch sensor or our hearing sensors. So these sensors, when they receive signals, these signals basically are processed inside our brain, which is our main decision-making part of our body. And until the signal reaches there, the system inside add to it certain firing and certain constants so that train your system. When you receive this sound, that sound is a crying baby. When you receive this sound, this is a sound of a horse, and so on and so forth. So you have here your input data. So the data is discrete here. At the end of the day, your feature vector is numbers. And then you feed them to the network to predict something, predict class, predict anything that you want to do. Now, the neural network, we don't know exactly what is happening. You try to map. You say, okay, this is one feature vector. You said that this vector, if the partial discharge, it is internal. This feature vector is the partial discharge internal. And you feed many of those. So the neural network, it will adjust itself by creating nonlinear functions to map your input to your output until it is well trained and it has a model that can really map this to the input vector to the output. Then you enter your second class, your third class, and so on and so forth, until you have a very good, well-trained model. How did that? You have input layer, you have hidden layers, you have actually, these are some nonlinear, the most common one called the sigmoid functions. So you try to have a mathematical nonlinear function between the output and the inputs using constants, using nonlinear functions. As I said, the adjustment of this is done automatically. You don't need to worry about it. Once you have the model ready, then you can basically test it the way I just mentioned. Another classifier is the support vector machine. Support vector machine is basically used for a two-class problem, but it can be used for three-class problems. So here you have the data. So this is your data. These pluses are basically one class, and this is negatives are basically another class. So you try to have a margin between them, a boundary between them, okay? And you try to maximize the distance. So here, and these margins are vectors. So this is what I call support vector. So we will have here this vector, isolate all these classes, and this vector, you isolate all that classes. And you try to maximize the distance, but to include all the classes in one side. And you have this area as basically a separation hyperplane. So, and then you see if you bring a new sample, the testing sample, where it comes. Does it comes in that region or in that region to classify it? If it's something in between, then the system will try to figure out it's closest to which region. But before that, you have to basically, you try to create that. Now, sometimes, and in many times, these two classes are basically overlapping each other. So there are certain tricks that we apply trying to separate them and make them easy to be identified as two different classes. Now, what if we have more than two classes? Let's say we have three classes. So you have a model that you combine class A and B as one class, and then against class 3. And then you keep doing this until you have a model that can differentiate between all the classes. The third one is the KNN, K nearest neighbor. So here, let's say you have this system, you have class, the blue, okay, and the red. So these are classes here, spread, this is your training, and then you bring something like this. And this you don't know, does it belong to the red or bring it to the blue? So what you do, you measure the distance between this unknown to the closest ones from both classes and see, does it belong to the red or to the blue? If it closes to the red, then basically it's a red class. If it's closest to the blue, then it is a blue class. Then if you come here and you measure the distance between this and this is the distance, okay? So this is the distance, this is the closest blue. So it's obvious it's a red class. Sometimes you have an outlier, okay? So instead of measuring the distance between one class or one point, you measure with the 3. And then you see, so for example, you measure between this and you add to it this distance, and then you add to it this distance. And for the blue, you measure with this, with this, with this. Now, when you increase the number of points, you increase the robustness of the model and make it basically closer to the class. So now, if it is closer to the blue, okay, maybe these are outlier. Maybe the red class is only here, and the blue is here. This is the blue case. This is close to the blue. And these 2 points are not basically part of the red. They are just some bad data, okay? And this bad data will lead to bad classification. So if I increase the number of KNN, so we use what we have KNN 3, so we connect, or KNN 5. These are the most common. So you measure it with 5, 1, 2, 3, 4, 5. When you do that, clearly this now belongs to the blue stage. So only KNN1 sometimes give you good results. It depends where is, for example, if this point was here that you don't know. Okay, so even if you take only one, so it's obviously belong to the red, and this is correct. Okay, because it's far away from the bad data. Okay, but to be on the safe side, if you do it on, for example, for 3, see here, this is 3, and here is the 3 data points that you measure. Again, it is also with the red. Now you built your model. Now you want to test your model. How to tell if your model is good or is bad? So there are certain metrics. We use them for the classification. The first one is the accuracy rate. Okay. Now, before going to the accuracy, let's understand these terminology: TP, TN, FN, and FP. What do they mean? True positive. Let's say, for example, here you are classifying between if this is, let's say, a partial discharge or noise. So that is your problem. So it's a two class. It's either PD or noise. So true positive means that you classify it as PD and it was actually a PD. That means true positive. True negative, it's not PD, so you classify it as noise and it was actually a noise. Then the false negative and the false positive is the opposite. False negative, yeah, that you said it is a noise, but it was not a noise, it was a PD. So this is called false negative. False positive, you said it's a PD, but it was not PD, it was a noise. So that's the meaning of those. So here this is the most common metric that we use, which is the accuracy rate. How many the true positive, how many the true negative you have, divide by all of them. This will give you the overall accuracy. This is a very good measure. It has been, this is the first one. You see that you will see that, okay, that classification accuracy is 85%. It is 92%. That's what exactly means. However, sometimes that's not a very good measure. Why is that? Because sometimes one of the classes is very good classified, or three classes well classified, and only one is bad. The overall accuracy looks good, but it's misleading. So we need to have two more measures. So we have something called the precision, the recall, and the F1 measure. This is a combination of the two. So the precision is the true positive over the true positive plus the false positive. How many true positive that you have as opposed to the true positive plus the false positive. And the recall is the true positive with respect to the true positive, but the false negative. Now, we put these things in what we call the confusion matrix. Okay? So this, let's say means that this is PD, and this is noise. This is PD, and this is noise. So true positive, it means that it was really a PD, and it was classified as a PD. So you want this number to be as high as possible. True negative, it was a noise, actually a noise, and classified as noise. Also, we want this to be as high as possible. So we want the diagonal elements to be very high values. Now we look to the off diagonal, we want them as low as possible, because this is where the confusion happens. So here it is a false negative. So it is basically a PD, but classified as a noise. Or false positive, it was actually a noise, but classified as a PD. So these two numbers, you want them to be as small as possible. So when I look to the confusion matrix, if the diagonal element is very, very high, it means that I have very good. Plus, it tells me where is the confusion, where is the classes that overlap between each other. So that is an overview of the outdoor about machine learning. Let's have a short break. Let's say 5 minutes, and then we'll come here after this introduction to do sort of basically we will do examples. Hi everyone, and welcome back. Okay, so now until the end of today's lecture, I will just be presenting cases. Okay, now we understand the foundation, what is machine learning. So whatever I mentioned here, I will try to basically apply it here. So I divided this into two different parts. With the first one, will start with ceramic insulators, and in the ceramic insulators, we will detect physical damages using RF antenna and ultrasonic sensors. So we'll have two problems. And for the evaluation, we'll try to basically estimate the NSDD, the non-soluble deposit density. So we have three problems. These three problems, I have the data. We will apply the machine learning algorithms basically to and we will do that. We will basically not just present it, but we will show you how to apply that using Weka. Okay. So as we know that the age of ceramic insulators is basically now, especially in North America, they are extremely old, and many of them, they have exceeded their life expectations. We have around 150 million estimated. We have it in North America. Now, the cost of those insulators compared to the overall cost of the overhead lines is very small, 5 to 8%. However, 60 to 70% of the failures coming from those insulators. So in this study, we try to detect damages, corona, crack, internal defects, and so on and so forth. So that is the overall block diagram of the problem. So we have the insulators here. So what we do, we bring an insulator with a known defect, energize it, it will start to emit ultrasonic, emit RF. So in one problem, we use the RF antenna. In the other, we use acoustic sensors. Now, this is how the RF signal look like. This is how the acoustic signal, and I will come to the description of these signals later on. From the RF, we will extract statistical features. From the acoustic, we'll extract the F of T, and then we'll do the classification. This is basically the specifications of the sensors. So the acoustic, this is the brand name, and it has a 40 kilohertz as center frequency, and the range is from 16 to 80 kilohertz. On the other hand, the antenna from 1 to 2 gigahertz and has a gain of around 14 to 18 decibels. Now, in this, basically, we will use the 60, 120, 180 hertz. Here, this was done for a different problem, but here we'll use only the kurtosis and the skewness of the signal itself, not the wavelet. And here we'll use to detect corona, crack, and wet surface discharge. So it's the three-class problem. Here we'll detect corona, crack, and hole. So also a three-class problem. So let's start with the acoustic. So this is the acoustic sensor we used. These are the three insulators. We have a surface crack here, as you can see. This is the surface crack. We have pollution, okay? But also we have here a sharp point to generate corona. Why? Because when you are in the field, corona sometimes is inevitable. You will measure it. So we want to include corona as well, so that we make sure that the sensor will not, for example, detect corona and think this is a defect. We have one disk of insulators, and as I said, every time we have a known defect, energize it, then we use the sensor, collect data, many data as much as we can to for the test object, that specific defect, change the insulator with another defect, energize it, collect the data under the other defect, and so on and so forth. Now, the sensor itself has some pre-processing unit inside it. We did not do that. The sensor itself does that. So this is the original acoustic signal. It has, it apply high pass filter, and it will take the envelope of this high frequency component, and then it will find or demodulate the signals over the 60 hertz component. So it's always giving you 60, 120, 180 hertz. These are the most important frequencies. So we have only 3 frequency components, and every time we detect that. For example, this is a typical signal, and this is the frequency content of it. So this is the envelope of the signal. So this is basically at that stage. We can measure this and we can measure this. These two are basically saved, but we cannot measure the raw data. And we can see here, this is basically the frequency components. Now, when we put the data here, okay, So this is the 3D presentation of the data. Corona is this is the corona, and then discharge from a crack, porcelain, and from the contamination. So the blue is the crack, and the green is the contamination. So you see here, this is one class. There is an overlap. So by just looking to the data, you think that okay, I think here we'll get a very high accuracy, maybe 100%, but they are overlapped with each other. Having said that, now let's go and let me now go to Weka. Now this is Weka. As I said, this is the software that we'll be using. And Weka, as I mentioned, it's a very nice, interesting software. So you just need to just search it and download it. You go to Explore. We have many options. We only need the Explore option here. Take this down here. No. Okay. So this is my Weka here. So I need to open a file. The first thing you need to open the file. Now here, let me show you the data that I have here. So I have all the data here. Let's have a look to the data. This is the data. So we will have, this is the acoustic signals. We have two problems. I will use only this one. So let's see how we put the data there. This is the type of discharges. Okay. So we have here the 60, 120, 180 hertz. This is basically the feature vector. And here the defect type. So this is corona, 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 corona. All of this is corona. And then we have surface cracks. We have 100 points for corona, surface crack, and then polluted surface. So we have equal classes, 100 each. Okay. And now we understand how the data look like. Let me come here. Okay, now let me open the file. I will go to YouTube, the folder I have them, acoustic. Now I have to change this to CSV. There are different formats of the data. CSV, you can create from Excel. This is the easiest one. So you come here and open. Now you open the file. So you have here the feature vector, the 60, the 120, the 180, the defect type. You look here, the presentation of the data. So we have corona 100, surface 100, polluted 100. Now here show you the 60 hertz. The minimum value is 0.2, the maximum is 20.1, the mean and the standard deviation. So it gives you all these statistical information about this. It is really a very nice software, and I shared some of the data with you if you want to work with it, but I will not spend much time here. I will just, you have the feeling. Now, once you uploaded the data, you go to classify. And here you choose the classifier. There are tons of classifiers here, okay? So here, for example, the multi-layer presbytone, this is the neural network. So you select this one. And then how you want to, this is the percentage split. As I mentioned, you can split the data. Now, because the data is not large, cross-validation is better. What is a cross-validation? You split the data into 10, you split the data into 10 different configurations. How is that? You have the data, it's 100 points. You keep 90 for training, 10 for testing. And then this 10 for testing, you add it to the training and you take another 10% for testing. And you repeat this. And you do that 10 times and then you take the average of this. So this cross validation tenfold, it's called, this is one of the best to do that. Now, click here and let me have the hidden layer as 1. We'll just add this. Okay. And that's it. This is the only thing I will play with. Now, start. And here comes. Now, here is the classification. It's 84%. This is your classification accuracy. Okay. Now, when you look to this is the confusion matrix. Corona, 100%. There is no misclassification. And that's what we expected. And this is something very important that you need to look to your data so that you really understand it before you apply any machine learning algorithms. So it seems that the frequency content from the corona is unique compared to the dry and the surface crack. Here, the surface crack, you see here that there is misclassification. We are getting 84%. Okay, come here, change the header layer, make it maybe 2, and see what will happen. Okay, this is 84. Let me start with 87%, a better accuracy. Still, the corona is 100%. And here you can see that you have misclassifications happened here. You can come here and choose a different classifier. So let's use the KNN. KNN is called IPK here. So let me play with it. So this is use KNN 3. Okay. And start. So we get 85%. So neural network gave us a better. Let me make it 5 maybe. See if any improvement can happen here. This is 85, start 87%. Okay, so it is close to the other one. And always you will see that the corona, regardless of the classifier used, it is basically 100%. One of the good classifier that I don't talk about it, which is basically the trees. Sometimes it gives good results, like random forest and start. So it gives you not better. As I said, there is no magic classifier that is good for everything. Okay, there are some good classifiers, and there for specific data, a better classifier for a different data, and so on and so forth. Having said that, let's go to the second problem. The second problem will use the RF. This is the RF antenna I told you about. I want to differentiate between corona, surface crack, and internal void. Now here, I did not use the wet surface. And that's take us to, again, the point I was trying to make today, which is you have really to understand the physics of your problem. Why I did not apply the wet here? I did not apply the wet because the wet gave you low frequency emission. Low frequency electromagnetic waves cannot be detected by an antenna. So it's not, and actually I did some measurement there and you cannot see anything. Unless there is a plasma, because you have very severe dry band arcing, plasma will create high frequency components. But if the dry band arcing at the early stage, you will not detect anything. Now, why I did not, this is internal void. This is something very important because once ceramic insulators start to get deteriorated, you will start to have some holes inside, which will lead to partial discharge, maybe complete failure later on. I did not use the acoustic to detect internal. And the reason for that, whenever you have an internal discharge, the acoustic signal will be absorbed by the surrounding. It will not be emitted. But the RF antenna can penetrate. And that is one of the advantages of the RF compared to the acoustic. And the acoustic has an advantage that can detect the low frequency, the RF antenna cannot do that. So this is a typical signal. So for the signal, what we did, we found only the skewness and the kurtosis, only statistical features. And it was a low number of data. That this problem is actually for only demonstration. The previous problem, it was a master student work. But this one, I just did it just to demonstrate to you. So I have this signal, has a lot of points. So I just use the skewness and the kurtosis from that signal. So we'll have a feature vector that has 2 points only. And here is basically your discharge type. So let's now go back here to our classifier here. Now let's go back to the preprocessing. Let's open the files. Now let me go and select the RF signal. Here it is, open. So now it removed the previous one. Now we have here. So we have the skewness, the kurtosis, and the discharge type. So we have 20 corona, 20 surface crack, and so this number, and if it's not balanced, so we don't expect to have a very good results here, but nevertheless. So let's see to classify here. So let me use basically my multi, and let me use one in the layer. Okay. And let me start. So we have 80% classifications, and you can see here the surface crack is basically doing very, very well. It's not misclassified with anything. The problem is with corona and the internal. Now, if we come here and let's see if I make this 2 hidden layers instead of 1. Okay, and this we do the classification here, start. Okay, better, 84%. Now, the surface crack, now when you increase the accuracy, it has one misclassified signal. Okay, now, as I said, this is the beauty of this software. I don't know coding, you don't know coding, you can just try, play with the data, as you can upload as many cases as you want, and you can do the classification and then see which one give you the best results. But again, this is a bad data because a very small number of data, so your classifier will be very, very much biased. Always you have to have large number of data and at different conditions. The more conditions you have, the better. Now, I have a PhD student, Abdullah, actually, the one that you're working with. He is working using acoustic sensor to detect different types of damages in ceramic insulators. Now he is gathering tens of thousands of data points. So it's a huge data. Okay? But he used something, not machine learning, but he's using something called deep learning. I will come to the deep learning by the end of the lecture, but machine learning so far is really good. Okay, it has a problem. You start to notice that I select some features manually. Maybe they don't work. Then I have to go and select another features and so on and so forth. Okay, so here it is. The third problem I'd like to talk about is about the pollution severity. When you have polluted insulators, okay, and especially when you are working early morning, there's no rain, and this pollutant has certain salt in it. If there's a humid day, like here we have some days are humid. Fortunately, here we have raining in Canada, so raining wash the insulator, which is a good thing. But if it's just dew, then it start to have an electrolyte that start to be dissolved, then you will have surface discharge that can lead to a flashover. So to basically identify the severity, we mentioned that before last week, we have the equivalent salt deposit density and non-soluble deposit density. So how to basically quantify this? You wash the insulators, deionize water, collect this pollutant. Then if you measure the conductivity, you can find the ESDD. You measure the pollutant, the inert material with respect to the surface area, you will find the NSDD. So here we're trying to basically have a non-contact method using only images, trying to basically classify the NSDD. So we have the insulators, ceramic insulators. We prepare as per the IEEE and IC standard a certain slurry. We basically dip the insulator there, take it out, and this slurry has different concentrations of pollutant, and then make it dry, and then take images. So this is, for example, an image for a clean insulator, and this is for an insulator with a pollutant on it. Okay. Then we changed this is our sensor. Here is a regular camera. In the previous case, it was an RF antenna and ultrasonic sensor. Here is just a regular camera. Okay. And then here we are changing the images from colored one into a black and white. Okay. And then we calculate some, this is now the feature extraction. I cannot just feed the images as they are in machine learning, but I need to extract features. So we found that, and this is by understanding the nature of the problem, that when you have a pollutant, that the insulators basically will be like white, the color of those insulators will be basically lighter. Okay, so if we find the histogram of the tonal value, okay, and then trying to find the features here was the area of the first tonal number, first 50 tonal numbers, and then the medium of this. Okay. Okay. Now, when the insulator is clean, you will find that the first 50 numbers, which are darker, okay, they have higher number compared to the when the insulators are not polluted, when they are polluted. And the mean value here is higher than this. The mean value of the tonal value is higher than the one that is not, basically, because as you go in the whiter range, it's getting higher and higher. So when you have a polluted insulator, the tonal value would start to increase. Okay, so we took these two features only, and when we draw them against each other, the global mean, which is this number, and the area of the first 50 tonal, and we have identified 4 levels of NSDD. So we see this is the clean one are isolated from the others, but you can see here that the classes are separable. So we are expecting here to see a good evaluation. This is how the feature vector look like. We have a global mean and we have an area. Okay, so these are just numbers, and here's the classes: clean, clean, and we have the four levels. So this is the last example I want to show to you using our Weka. So I will go here again, pre-processing, open the file, and then we will go here up. We'll go to the NSDD classification. This is the NSD class. Open it. So this is the global mean, the minimum, the maximum, the mean, the standard deviation. This is the area of the first tonal numbers, and here's the classes. We have 4 classes. Each one is 24 cases. So again, go to classifier here. So I will use the same neural network. You can use this one. Okay, right away. Start. So you have 87.5% when you have one hidden layer. Okay. And you can see here the first class, which is a clean, it is 100% correct. And we have seen that because basically they are away from all other classes. If I use the second neural network, which is this one, which has basically 2 hidden layers. Okay, start. It's 87.5%. Okay, better accuracy, and so on and so forth. And as I said, you can try different classifiers until you find what is the best classifier that will lead to the best results. Okay. Now, as I said here, it's very important. This is again, that was like a capstone project. If I want to do this technology, apply it for real field problems, there are many issues I have to take care of. For example, I take the images at internal or at actually indoor conditions. When I take the images at outdoor conditions, the lighting conditions will change, and this tonal number will be different, and this will ruin the whole classifier. Okay, so this is something very important I have to pay attention to. So I have to have my model applied for indoor and for outdoor. And even for outdoor, sometimes there's clouds. This will affect my my system or my images, and this can affect the classes, and so on and so forth. Here in this problem, I only assumed one pollutant, one color. What if the pollutant has a different color? Then the problem becomes more and more complicated. Maybe a solution for this, you can have different models, depends where are the insulators, because depending on the location of the insulators, you will have different pollutant, will have different colors. So then you have to have maybe a different models for that. So this is what I want to say here. It's nice to get good results here, but once you start to target, to solve actual problems in the field, things becomes more and more complicated. Now, for non-ceramic insulators, as we talked about this before, this case, their aging is enemy number 1 for those insulators. So here we have 2 different problems. I will talk about them. The first one is to predict the hydrophobicity, and then the other one, internal damages. I will talk about each problem by itself. But here I don't have the data for this, so I will just present that just as an regular presentation, but you get the point. You get how to apply your machine learning. I have some small presentations, and there's a link for those presentations. You can click on them and you can watch the full videos. So the hydrophobicity, we know that this is the ability of the material if it's to basically repel. When you have a hydrophobic surface, the water will be like away from each other, and you have a hydrophobic surface which will not allow any leakage current to develop on the surface. As the material age with time, you start to move from hydrophobic to hydrophilic. And here's the standard, STRI standard adopted by the IEC standard, comes up with this. So this is hydrophysics class 1, which is the best. And this is number 6, which is very, very bad. And in between, there are some certain classes as well. So this is a very interesting image processing problem. So I gave this problem to one of my master's students. Before that, we gave it to an undergraduate student as a capstone project. And we said instead of, let's say, 6 classes here, we will combine 1 and 2, make it one class, 3 and 4, another class, 5 and 6, and 7. There's a 7 when it's completely wet as the third class. Okay, so now the whole idea here, how to take this problem from an image into basically a machine learning problem. So the first thing, you take the images. Second, you have to extract features from those images, and those features, you should represent the phenomena from these images. So this is the setup that we built, okay, and we have like an online system. So you can basically just, this is the samples, and here is a water sprayer. The standard asks you to spray the water at certain distance, and then take the image and see how is the water droplet is distributed. So they build an automated system for that. You take the image, send it to the classifier here, and then the classifier will basically give you if it is good or it's bad or it's medium. So how they did that, first you take the images, and then using edge detection algorithm is applied to find the black and white images. So here you take these images, these are image processing techniques. So this image is transferred to this. So this is what we call the pre-processing stage. Then we find something we call the gray level co-occurrence matrix, or the GLCM. What is this matrix? When you go back here, you do the pre-processing, the whole image is black and white. And these are pixels, basically. So you divide these images into 2 pixels each, blocks of each 2 pixels. So these 2 pixels could be white, 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 black, black, white, black, black. And the black and white will reflect. For example, if you have too much of black here, it means that this is mainly wet. If you have a lot of white, it means it's more hydrophobic. So we found after investigation, after studying the images, that this could be a good feature to extract. And then you count how many white, white, how many white, black, how many black, black, and you came up with a matrix like this. So this is the co-occurrence matrix. This is 4 by 4, 2 by 2. So basically we take the images like that. So this represented here. This is the counting of the black and the white. And you can see here this number, for example, is different than this number, is different than that number. Okay. This is for the black, because we have here more black pixels, count them, and so on and so forth. So the whole image now, it changed into a matrix, numbers, that's it. And when we apply the system, we get a very good accuracy, because the 3 class problem, they are separable. You can see here, they are far away from each other. And here is the demo for the system. You can click on that. I will just show it to you here, the link. So here, basically, we spray the water. Okay, so the water is sprayed on the surface. We will take the image to the system here, capture the image. Okay, here is the image. This is good class. Process it, give you good. Now, this is another image here. And when the system is bad, hydrophilic, take the image, spray the water, capture the image here, and then do the classifications. It's really bad, as you can see, and give you bad. So this is what you see here, but behind that, this comes the algorithm. We expand that to a 7 class problem. I use a master's student to do that, and he get very, very good results. Now, So far, this work was done on a controlled sample. I expanded the work when I came here to Canada, and now trying to actually to do real insulators, coated insulators, indoor, outdoor, different insulator colors, and this gave more and more challenging to the problem, but we solve it in a different approach. I will come to it at the end of the lecture. The last thing, or the last problem we're trying to solve here, is trying to detect defects inside non-ceramic insulators. So if there's a crack in the fiberglass, or if there is some during the processing, the manufacturing process, if any metallic particles went inside between the core and the rubber when you do injection molding, or if there's a poor bonding between the rubber and the fiberglass, which will lead to some air gaps. Also, we want to detect that. So these are three problems can happen in the factory. So we want to come up with a technique to detect these ones. There is no viable technique as per the IEEE standard that can detect all these problems. So we will try different things like using the Megar test, partial discharge, leakage current, and so on and so forth. You don't find any technique that can measure all these type of typical defects in ceramic insulators, non-ceramic insulators. So we came up with this technique. This technique basically we just trying to produce a very high frequency signal. So we have a detector that we have a waveguide, and this waveguide generate very high frequencies. So these frequencies will go there, and it will be basically part of it will be absorbed, part of it will be reflected based on the structure of the material. So if you have voids, if you have crack, if you have metallic inclusion, the amount of the signal that is reflected will be different. And here's the detector diode that detect the reflected signal, take it to your DAC to measure the signal. So here shows you the system. This is the insulators, here the waveguide. This output here. This is the effect here. So we found that we can detect something. So we try to classify this, and we got very good results. We get 95% classification to distinguish between these three defects, between metallic, between air void, and between if there's no defect at all in the insulators. Also, we could generate a 3D image. So if there's a metallic inclusion, we have an image something like this. If it is a crack, we have something like this. If there's an air void, we have something like this. So this technique can be utilized by the manufacturer for quality control. So before the insulator leave their factory, they can scan it, or they can apply machine learning to it and try to detect any type of defects. Okay, so to sum up, or this has come to the conclusion, what is the new trends now in this technology? Application of machine learning. One of the things that people are trying, many researchers are actively involved, and I am also trying to get into this area, is to use UAV, you use drones to do some inspection of the insulators. So you have the drones here, you equip them with certain sensors, and then send them close to the insulators and do the inspection. With this, it is more efficient, it is safer, because the current technique, you send people with helicopters or with from the ground level, they go and start to watch and try to find the problem there, which is very difficult, even if you have the sensor. But if you have the drones, you can come closer and you can do all the measurements. So you equip all the sensors that you want. It could be ultrasonic, RF antenna, IR camera, UV camera, regular camera, regardless. And now the new trend is trying to do the classification on board, meaning that you have a microcontroller, you receive the signal, you do all the machine learning algorithm, and you come up with a decision. Oh, this insulator is polluted. Oh, this insulator has a crack, has a physical damage. Oh, there is some corona here. Okay. And then you communicate that to the engineer. Now, the ultimate goal of this technology is to have autonomous drones. That is still a very ambitious goal. What does mean? You are a utility engineer, you send your drones all once, and you provide them with the GPS coordinate of your transmission lines. They are not basically guided by anyone. They go there, do the inspection. Whenever they find a problem, they record the GPS coordinate of that tower and send it back to you. You receive the information. So that is the ultimate goal of this technology. Now, currently, people using the drones manually, controlled manually. So you have an engineer go there beneath the tower and you control them and just collect images. They don't even apply machine learning for the drone. The application of machine learning is done all offline, not in real time. So this technology and this way has a lot of potential to be applied. The second thing is the application of deep learning. And that is basically what I'm switching now from machine learning to deep learning. What is the basic difference between machine learning and deep learning? In machine learning, basically, you have your input signal or images. You have to extract features as we have seen. In deep learning, no, you feed the images, you feed the signals as they are, okay? And the algorithm will extract the feature for you. So you don't need to worry about this. And this will make the process much, much easier. I'll just give you an example. The problem of the hydrophobicity, I gave it to you before. It took my master's students more than 6 months to come up with the right features, another 2-3 months to apply the algorithms. I give the data set to a second-year electrical engineering student, and he doesn't know anything about high voltage engineering. And I asked him to use deep learning. In less than a month, he solved the same problem, and he got very similar results. So that gives you how efficient is this. The only drawback of the deep learning that you have to have a huge number of data compared to the machine learning. So if, for example, if you need 1,000 images in machine learning, you need 100,000 images of deep learning. Sometimes that's not possible. How you can get 100,000 images of each class? The people came up with something called transfer learning. They bring to you a well-trained neural network. They call it convolutional neural network. This is one of the most famous technique in deep learning that is trained on different images. And then you come to the last layer and you just change that and make it suitable for your system. So basically, by using a pre-trained neural network, you don't need to retrain everything. And then by just changing the last layer, it make it custom to your application. And this technique is working really very, very well. I can see that deep learning is the future of machine learning. I think soon it will replace the machine learning completely because it is much more efficient, much easier to deal with. And because now your algorithm is the one selecting the features, so most probably it will select the best feature for the problem. Okay, that's what I want to say today. If you have any questions, please go ahead.